decimal is not your remainder. So there were 3 steps to this, 2 technically. First thing we got to do is take our 9-digit number and divide it by 7. See how many times 7 goes into this number evenly. That was 915, 754, 923, divided by 7. Punch that in your calculator. And you get 130, 822, 131, and I got 0.85714. Now, that decimal at the end, like I said, that is not your remainder. Instead, what you need to pay attention to is this part right here. So 130,822,131 is how many times 7 goes into that tracking number evenly. So, to find the remainder, the next step is to take the 130,821 times 7. Okay? This will give us the multiple of 7 immediately beneath that 9-digit number. So 130,822, 131 times 7, I got 915,754, 917. So, if you compare your original 9-digit number with this one from step 2, you'll notice there's a difference of 6. We write that mathematically, subtract them. Which means 6 would be your 10th digit for the tracking number. Which means 6 is your check digit. Which means 6 is the remainder when you divide those original 9 digits by 7. Okay? Yes?
FedEx, is it always, you always divide by 7?
Yes.
Okay, and you say 6 is a check digit, but 6 isn't in your numbers. What, is it -6 at the end of that?
Yeah, it'd be something like that. It's always, like with UPC codes, for example, there's always one extra number at the end that sometimes you're like, I don't understand what this has anything to do with if you work retail. It's check digits. Same principle.
But it's only FedEx that we divide by 7.
Yes, for this type of problem, if you see the word FedEx tracking number, this is the method you'll use. You divide by 7. Exactly. Okay, so there's one version. Again, keywords on the test if you see, find the check digit for the Federal Express package with tracking number blah, 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 blah. You do this one. Now another version. UPCs, you can use codes. Okay. There are several categories that a UPC code is broken into, right? If you look at your see. Why am I numbering off?
Last week you did it 1
You
plus
just the one at
1.
the bottom.
Oh, I'm looking at the wrong one. That's why. Thank you. You're like, where are my notes on? So remember this one: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. That makes more sense. Okay. So starting over. Odd positions. We've got the 1, and then in position 3 is another 1. Position 5 is a 0. Position 7 is another 0. Position 9 is a 1. And position 11 is another 7. So it says sum the digits of the odd positions and multiply by 3. So times 3. Punch that. You don't even need to punch that in a calculator. That becomes 10 times 3. You get 30 for the first part. Yes? Okay. Step 2. Sum the digits in the even position. Okay. So position 2 is a, let's see, we got a 3 plus a 0 in position 4, a 0 in position 6, 0 in position 8, and 4 in position 10. That gives me a grand total of 7. Okay? So for step 3, what we need, when the check digit is added, the total must be a multiple of 10. Well, so far we've got 30 plus 7 gives us 37. The next multiple of 10 up would be 40. So you have to add 3 to get 40. The number that you add to get to the next multiple of 10 is the check digit. Whatever number you add to the sum from steps 1 and 2 to get to the next multiple of 10 is the check digit. Questions on the UPC process? Next. International Standard Book Number. Pretty sure we're familiar with this. We've had to buy textbooks for classes. Okay. All right. This ISBN number, another 10-digit number. Okay. These numbers are evenly divisible by 11. Okay. So it's kind of like a mishmash of the FedEx and UPC code. You take your first 9 digits, right? Add them up, and then whatever you get to, you add however many numbers to that to get to a multiple of 11. Just like in the last one, you add a number to sum to get to a multiple of 10. For ISBNs, you want a multiple of 11. Okay? And then, of course, there's the ISBN 13. Pretty sure we're only going to use the 10 for this class. All right. We have that number. Here's a way of working backwards for this. Did I miss the slide? I think I missed the slide. Oh, there it is. That one. Okay. So, we have 10 numbers, right? So we take each number position times the number in the ISBN, meaning this. Okay, you can look at the formula right here. That tested at 8:20 a.m. That's way too early for me. Step 1. First position, you take 10 times our first value, which is a 1. I'm looking at the ISBN in blue. Next position, plus 9 times the next number would be 2. 5. 7 times 6. 6 times 7. Next position is 5. So we've got 1, 2, 5, 6, 7, and then another 6. 4 times a 4. 3 times a 4. And 2 times a 7. Now remember, the last digit is left for us to figure out. So, punch all this into your calculator. You should get a grand total of 208. Nope, wrong again. I've got 224. Let's double check that. So, 10 times 1, 9 times 2, 8 times 5. Anyone else get 224?
Yeah.
I got 224. Awesome. Okay. So, remember the goal, you want your total ISBN to be divisible by 7 evenly. Well, 224 is not divisible by 11. If you punch it in, you get 20 and some change. Okay, so we need to find the next multiple of 11. Did I say 7 earlier?
You said 7.
It's supposed to be 11. Okay. You can go by trial and error on here. If you do 11 times 11 on your calculator, that's 121. So you're not quite there yet. So keep going. 11 times 15 is 165. Well, 11 times 20 gives you 220, right? You're using your calculator. 11 times 20 gives 220, but we need the next one up from that. So 11 times 21 gives you 231. 231 is the next multiple that is above 224. Okay. So, for your last step, you gotta take 231 minus 224, and that gives you 7. So 7 is your check digit. That's the number you have to add to 224 to get to the next multiple of 11. Okay, so let's run through that again. 10 digits in an ISBN number. You take the number position times the number itself. So 10 times your first digit, 9 times your next digit, 8, so on and so forth, all the way down the line. You won't have a 1 times whatever, because that last digit is what you have to find. Okay? So we add up everything from step 1. 10 times whatever, 9 times whatever, 8 times whatever, so on and so forth. Whatever number you get from step 1, you got to add something to that number to make your ISBN a multiple of 11. So you can use your calculator and go through trial and error, find the multiple of 11 that is directly above the number from step 1. In our case, the next multiple 11 was 231. So find the check digit, take that multiple of 11, and subtract from it the values from step 1. That's the number you have to add to step 1 to get to your multiple of 11. That is your check digit. Okay. Questions on ISBN?
I want to know what did you do, like 10 times 1 last time?
Okay.
I know that you use the numbers up there, but what did you do for 1 to go?
All right. So you get the 10 and the 9 and the 8, 7, 6, 5, 4, 3, 2. These values, the 1, 2, 5, 6, 7, 6, 4, 4, 7, come from that ISBN. So, yeah. So it's first, what is that? 9 digits of your ISBN 10, and the last digit is what we just found. Other questions? Some of these algorithms can get rather tricky. Does that make sense? All right. Now, with the ISBN 10, since we know the algorithm, the key things, once you do 10 times whatever, 9 times whatever, so on and so forth, you want your final number to be a multiple of 11. So we're going to bring this full circle with that modular arithmetic that we talked about on Monday, so a week ago. I know we've slept since then. Okay. Modular arithmetic. If a number divides another number evenly, what should your remainder be? 0. No remainder at all. Okay. Well, according to our process for finding the check digit of an ISBN, you can determine whether an ISBN is legit or if it's a knockoff. Okay. So, here's how we do that. Suppose we have that ISBN number. Is it legit? Well, start her off the same way that you do to find the check digit. So, 10 times the digit in first position, so that's 1. 9 times 4. 8 times 2. 7 times 9. 6 times 2. 5 times 4. 4 times 5. 3 times 8. And 2 times 0. Okay? But since we have all 10 digits, go ahead and add the 7 at the end. That's the difference for whenever we're checking if the ISBN is legitimate or not. Punch that into your calculator. Okay. 10 times 1. 4. 2. 7 times 9. 5 times 4. 5. 8. 2 times 0. Plus 7. Okay. Anyone else get 208? I got 208. Okay. Now what's the main thing about the ISBN? It has to be divisible by 11, which means you should get a remainder of 0 if this is a legitimate ISBN. So, on your calculator, 208 divided by 11 gives me 18.9090, so on and so forth. Because you have this ugly decimal at the end, that means that there would be a remainder. Fun fact, if you have one number that's off or an error where 2 digits are switched around in their position, it will be detected. We're not going to go through how to do that, but in terms of scanning them and figuring out what goes where, there is coding that detects the errors and can correct them. So if this number were a multiple of 11, you would not have this ugly decimal stuff at the end. You just have a solid 18. But since you got extra stuff tacked on, that means there would be a remainder, which means 11 does not divide this number evenly, so it's not a legitimate ISBN. Still with me? Kind of? Sort of? Possible exam question. Give me a second to write that down. And this is the end of the material for, I believe it's supposed to be homework 13. Is that right, Naraka? Okay, homework 13. For some reason it says 12 in the notes. ones and zeros. If you've ever coded anything, we've talked about this before, I'm sure. Things you need to know. Basic unit of computer information is the binary digit or bit. That's where we get that term bit. I know, it's rather basic for some of us. Bits are either ones or zeros. Okay. 8 bits makes a byte of data. Kilobyte is 1,000 bytes, megabytes, million bytes, gigabytes, billion bytes, and terabytes, trillion bytes. Okay. And for some reason, my slides are a little off, as usual. For digital transmission, here's what's going on. Say you're sending a text message. This gets encoded as a sequence of bits, and we call these strings. These strings go along with, like, say you're texting a word. There is a string of bits that correlates with that word that you're texting. Binary code, as I said, is one of the really basic ways of transmitting this information. And this acronym ASCII, we pronounce that as ASCII. Okay. Again, if you've ever done any computer coding, you've heard of the ASCII system. The American Standard Code for Information Interchange. The code for representing English characters as 8-bit binary strings. And as an example, for the capital letter A, in ASCII code, it corresponds to that combination of zeros and ones. Lowercase a, you have that string of zeros and ones. Now, since this is a math class, we do have to do a little bit of math with this. Binary addition. We talked about modular arithmetic. Since we're talking binary, that means we're dealing with base 2. 2 numbers at a time, zeros and ones. Here's the key thing you need to remember. When you have 1 plus 1, yes, that equals 2, but since we're in base 2, what's 2 divided by 2? 2 divided by 2 is
0.
1 with a remainder of 0. That's what we're looking for. Modular arithmetic. Yes, 2 divided by 2 is 1, but in modular arithmetic, we only look at the remainder. So 2 divided by 2 is 1, the remainder 0, which is why 1 plus 1 equals 0 with binary code. Right? So you're looking in base 2. Divide your answer by 2, the remainder is the number you're actually looking for. Okay, keep this in mind. 1 plus 1 equals 0 for binary. Compute the following. Add the pairs of binary numbers together. Okay, so working right to left, regular old addition problem. 1 plus 0 is still 1. We said 1 plus 1 is 2, but since it's binary, 1 plus 1 is equal to 0. And you get another 0. 0 plus 0 is still 0. 0 plus 1 is 1. Another 1, a 0, and a 1. Yes? Relatively straightforward, don't make it harder than it is. All you're doing is adding top to bottom, just like you normally do. There's just one exception. 1 plus 1 is no longer equal to 2 in binary. Okay? Same thing. Next problem. Starting from the right. 1 plus 1 is 0. 0 in binary. 1 plus 0 is still 1. 0 plus 1 is 1. 1 plus 0 is 1. A 0. 1 plus 1 gives us another 0. A 1. And a 0. Okay? That's modular arithmetic in base 2. Otherwise known as binary code. Gentlemen, I can hear half your conversation up here. If you want to have a conversation about something other than this material, please excuse yourself. Thank you. Okay? Questions about binary addition? Okay? So, adding on a little bit more about this stuff. All right. have a whole set of code words all the same length, we call this a block code. Okay? You have your code word, particular length, have multiple code words, it's a block code. Okay? So here's an example, 010, 011, 111, 001. It's a block code, right? Because you've got a sense of 3, and each code word has length 3. All coding schemes involve taking a message apart and adding extra binary digits that we call check digits, just like we saw in the last one. How you calculate them, of course, will vary. Now, parity, we talked about this a little bit. The parity of a number determines whether a number is even or odd, right? That was on Monday or Friday of last week. Okay. We can use base 2 modular arithmetic to determine whether a number is even or odd. Think about it. All even numbers, if you divide them by 2, will have a remainder of 0. Odd numbers, if you divide by 2, should have a remainder of 1. Hey, there's some binary code right there, 0s and 1s. Okay. You can add a parity check digit to your blocks of code, okay, according to how many 1s there are. If you have an even number of 1s, add a 0. If you have an odd number, equal 1. So this is for parity. And a T, if I'm going to enunciate. That's a T, not a T. For the parity check digit, you have an even number of 1s, touching 0. You have an odd number of 1s, touching 1. So, let's fill this in. For this first chunk of text, there's only 2 1s, that's an even number, so check digit is a 0. The next one, we have 2 1s again, even number, so the check digit is a 0. And for the last chunk, we've got 3 1s, an odd number, so the check digit is a 1. So, check digit for parity. You know how to find that. Know the vocabulary, know the terms, that way you know what you're doing when you get to the question on the test or homework. Now, here's the thing with coding. Sometimes there are ways to detect errors and fix them, and sometimes you won't catch an error at all. It depends on the method of detecting them. Okay? So, if you're given a check digit, right, you can determine if the check digit matches whatever your chunk of coding was. But, since it doesn't tell you anything about the placement, the position of the 1s or 0s, if they get flip-flopped, you'll never know if there's an error there. Okay? If there's an extra 1 or an extra 0, you can catch that. But it won't tell you where it is, where it's supposed to be. Now, the size of block code. Do you ever notice that sometimes you're sending your friend a novel of a text message, and it might take a little bit longer to send than your other little, okay, see you soon, okay, bye, right? The longer text messages take a while. That's because you're sending a gigantic block of code. So, kind of goes along with this. If you have an original message, and the message is k bits long, right? You have so much data, k bits. Once you add your check digits to each of these chunks of code, you get a new length, right? It's now n bits long, right? Add check digits at the end of each of your words, right? So essentially, your message becomes longer than it originally was, digitally. That means you have a kn block code. There were originally k bits of data. Added your check digits. It's now n bits long, so it's a kn block. So, k is the original. length of your message. So, like I said, if you send a quick text, hey, I'll be there in 5 minutes. Not much code. But when you send a message that takes up your entire screen, that's a lot of code, and that's going to be a lot more check digits to add. So, it's going to take longer to send. That ties into the efficiency of your block of code itself. We're at a very, very base level. So, to determine the efficiency of a kn block code, you just take k divided by n. So if you have an 8-9 block code, its efficiency would be just 8 over 9. The more check digits you add, that means you're transmitting more bits of information, which means it will take longer to transmit. Make sense? Right? It takes longer to add more stuff. Okay, let's apply this. What's the efficiency of a 5-9 block code? 5 over 9. That's it. Now, how many check digits are in a 5-9 block code? Remember the layout? Five is the original amount. 9 is after adding the check digits. So, how many check digits were there? 9 minus 5 gives us 4. Now, here's the thing about those check digits. Yes, you end up having to transmit more data, but with more check digits, it gives you more chances of detecting the errors and fixing them. Couple more things. The Hamming distance between two strings in a binary block code. We're leading into how to actually find and correct some of these errors. All you do is you take your two strings of code and you find how many places they differ. So, for this example, between U and V, let's rewrite V underneath. That's a 0, 1, 1, 1, 0, 0, 1. In how many positions does this vary? Do each of these codes vary? The first one, the second position, third position, fourth position, fifth position, sixth position, and seventh position. None of the positions match, right? So they're different in all positions. So the Hamming distance is 7. Okay. The numbers do not match in 7 of the positions. That's why your Hamming distance is 7. They're 7 digits away from each other. Away from matching. Okay, nearest neighbor decoding. We're going to get into a little bit more detail with this on Friday. Hold on, let me just tell you what's going on here. I know some of you are going to be ambitious to try to look at it. Okay, if you have a word, this word has a code, right? Has an ASCII code that goes with it. Now, if the word itself doesn't send, the ASCII code is what's going to get sent instead. A little technical. Sometimes, the wrong coding gets sent. But there could be another word that's kind of close to that code, right? But there could be another word that differs by a few other digits. Here's your code that's incorrect. Here's one of the words that it could be. Here's another word that it could be. Whatever word your code is closest to is the word that gets chosen to be transmitted.